It is a section 15.23, double integrals in polar coordinates. The polar coordinate system was invented by Newton. Here we have a definition, polar point. Points in polar coordinate system are defined by two parameters, r and theta. R is the distance from the origin to the point xy, and theta is the angle from the positive x-axis. So by using r and theta, we can express the point. For example, in this xy coordinates, we have a point, for example, 1 and 1. So that is a point P, and 1 and 1. And then x direction is 1, y direction is 1. Now, if you try to express it with polar parameters, then you have to measure the distance r, and we have to find angle theta. But we can easily find the r. R is from Pythagorean theorem, that is square root of 2, and theta is pi over 4, that's 45 degrees, so that the P can be written as in this way, that is square root of 2, and angle is pi over 4 in polar coordinate. And for that one, to indicate the point is in the rectangular coordinate, we sometimes write here sub r. So in polar coordinates, we have the distance r is square root of 2, and angle is pi over 4. Okay. Here we have formulas. You can convert from r theta in polar coordinates to xy in rectangular coordinates. And you already know this one. X is r cosine theta, and y is r sine theta. And from this triangle, now the hypotenuse has a length r. So this bottom is r cosine theta, and this height must be r sine theta. So x is r cosine theta, y is r sine theta. Now from rectangular coordinates to polar coordinates, we can get r and theta by solving these equations. This comes from the Pythagorean theorem. R squared must be x squared plus y squared. Once x, y are given, then you can find r. Now you can find the theta when x and y are given. Right? Okay. Before solving double integral problems in polar coordinates, let's consider frequently used trigonometric formulas. The angle theta can be defined in this way. First, we consider the circle of radius 1 centered at the origin. Now we chose an angle like that. Then measure the arc length. Once arc length is theta, then we call this as a theta, angle theta. The angle is defined in this way, so that this whole circulation is 2 pi, because the arc length, the length of the circle, is 2 pi. Okay. Once we have theta, then in this triangle, this bottom is cosine theta, and height is sine theta. And tangent theta is a slope. Pictorially, you can show tangent theta in this way. From this point, now the vertical line hit this line, and from this to there is the tangent theta. Okay. Rather than theta rotation, we may use x notation. So from this figure, now Pythagorean theorem says that this squared plus that squared must be 1. That's exactly this formula. And if we divide the equation by sine squared ax, then we can reach that one. Now these two are some extra formulas. Sometimes you have to use these formulas, but this comes from this general formula. For example, now cosine, okay, just let's try to consider from sine. Okay, now sine a plus b, a and b are general angles, then that will be sine a and cosine b plus now sine b and cosine a. That's formula. And for cosine, cosine a plus b, that one is now cosine a cosine b minus, and that is a sine a sine b. Okay. Now I memorized this formula, in fact, with this mind. Sine is vertical component, so that once you try to put two angles for vertical function, then it may not be stable, so that it's breakdown, and that is, in a sense, maximum possible complicated combination, sine and cosine, a and b, sine and cosine, a and b, and that is opposite way. There's a and b, but this is b and a. So this is a kind of maximum possible complicated combination. Now cosine is horizontal direction, so it is more stable, so that cosine and sine are making group and now play the tug of war, so that cosine A, cosine B, and minus, there's a kind of string, and sine A, sine B. In this way, I memorize it. Once A and B are same x, then you can reach this formula from the first one. Now from second one, you can reach this formula. Okay. Now these two will be used to a lot. Sine squared x is 1 minus cosine 2x over 2. Cosine squared x is 1 plus cosine 2x over 2. Now only the difference is the sign. Rather than minus, we are using plus for cosine squared x. This will be used a lot, but this one is obtained from this one and that one. Okay. From here, for example, now cosine squared x is same as 1 minus sine squared x. So that now cosine 2x will be, now cosine squared x is 1 minus sine squared. So that 1 minus another one. So that 1 minus 2 sine squared x. Okay. So we move this into, the other side and move that one. And then we can reach at sine squared x. Okay, we have here now 2 equal and 1 minus cosine 2x. Now we divide the equation by 2, then we have that one. And if this one is replaced by 1 minus cosine squared x, then now you can get this one. Sometimes it is a little bit confusing. Now, when x is 0, the sine squared x must be 0. So that 1, when x is 0, 1, cosine 0 is 1. So the whole value will be 1. Now, will be 0. And when x is 0, the value must be 1. Now, there's 1 plus 1 over 2. So it is 1. So that it must be positive, it must be negative. Okay, don't be confused. Now consider here sectors, arc length, and area. We already know that once angle is theta, then arc length is a theta. Now, once the radius is r rather than 1, then it is r times, okay, once it is 1, then the arc length must be theta. However, there is r, which means is r times scaled. So that, again, the arc length must be r times scaled. So that arc length is r theta. And area can be found quite easily. You may think the area of sectors like almost the same as triangle. And okay, let's draw a figure. Now that is a sector. Okay, that is a sector. Okay, that height is r. In the center, we try to cut the arc here, then same length over the same length, L equal r theta. Now consider the triangle and connecting that like that, and connecting the end point from here to there like that. Then the area of triangle is the same as the area of this sector. We can prove that this portion and that portion are the same in area. So that eventually we can get the area of a sector from this triangle. And height is r, so the area must be half times, and bottom length is r theta, and height is r. So from here, we have a half r squared theta. Okay. So for the area of sectors, you may think that here in the computation, you may get it like 4 triangles. Okay. Half r squared theta. Now we'll try to get integrals, double integrals over polar rectangles. Polar rectangle is given in this form. R is from A to B, and theta is from alpha to beta. So like in this figure, angle is from alpha to beta, and R is from A to B. So that is polar rectangle. Now, to get integral, we first divide the polar rectangle into sub-regions. In order to do that, in R direction, we have here the divisions. In theta direction, also the same. So that in R direction, this length is delta r. In theta direction, there is delta theta. So with m and n points, we try to divide the polar rectangle into subregions. So therefore, each point you have the value, that is now here A, which is R0, R1, R2, and so on. And also in angle, that is theta 0, theta 1, theta 2, and final one will be theta n. Okay. Now, we focus on one sub-region. Let's say there's Rij. So we have here, and zoomed in. For this one, let's try to find now for the Riemann sum. Okay, for the Riemann sum, we have to get the area of this region and try to find the function value, and from a point in this region, so that locally we try to find the local volume. These volumes will be added to get the Riemann sum. So that we have to get the area of this region. Okay, we can find this one quite easily. This R is Ri minus 1, and that is Ri. So the area can be found in this way. Half Ri squared delta theta, that is delta theta. And so that whole area minus this less shaded area, that one, almost white area. And so that delta Aij is the same as that one. Now we rearrange it. Delta theta is common and half is common, and that is Ri squared minus Ri minus 1 squared, which can be written in this way. Now Ri minus 1 is delta R, and for this portion we name it Ri star. That is mid of this Ri and Ri minus 1, that is Ri star. So the area of this sub-region can be gotten along with this formula, Ri star times delta R and delta theta. Okay. So here, when we try to get the area, the Riemann sum will be double summation in R direction, theta direction, and F at some typical point times Ri and delta R, delta theta. Of course, we can put here theta. In this way, Riemann sum is defined, and we take a limit in R direction and theta direction, then that can be changed into this form. Okay, the function f in terms of r and theta rather than xy, and that will become r, that will become dr, that will become d theta. So we have this theorem. If f is continuous on a polar rectangle R and given by and this way, so it is a polar rectangle. Then here we have the double integral over R, the polar rectangle, can be found by using this iterated integral. Here we have to put R in from aerial computation. We have R, so you should not forget this R. And f of xy as a function of r theta, and r is moving from a to b, and theta is moving from alpha to beta. So by computing this one, you can get the double integral. Okay. Here we have note. Don't forget the R before the R and dr d theta. And also, okay, look at this one. Here we have delta Aij, the area, that one. If we consider this one as a rectangle, then that will be delta R, and R, in R direction is Ri, so that the length will be Ri times delta theta. So this times that one side, that is another side. If you multiply these two, then that is same as Ri, delta R, delta theta. So that simply, if you assume this is rectangle, then you can approximate the area of the sub-region in this way, so that eventually you can get, through the Riemann sum, you can get the same formula. Okay? So the reason I'm saying this one is that just for you to understand that the integral more thoroughly. So eventually dA is changed into R dr d theta. dA is aerial component, and also that is the same as the aerial component in polar coordinates. Okay. Okay, now we'll go to problems. Evaluate this one, where R is region in the upper half plane and bounded by two circles. Okay, let's try to visualize the region. Okay, now that is x direction, y direction. Okay, for that one, now it is in the upper half plane, but radius 1, like that, and radius 2 circle. Okay, so there is 1 and 2 upper part, so that's the region R. Okay, for this one, this is a polar rectangle, and here R is moving from 1 to 2, and theta is moving from 0 to pi, right? Okay, so it is a polar rectangle. So the given integral is the same as integral. Now theta integration, outer integral, you have to choose theta integral outer. So it's from 0 to pi. Now R is from 1 to 2. And for that one, you have to express it as a function of R and theta. That's 3. X is always R cosine theta, and Y is always R sine theta. So that there's 4 R squared and sine squared theta. And don't forget R and dr d theta. Okay? Okay. Now, from this one, from 0 to pi, we focus on inner integral. If R is multiplied here, then that is 3 R squared, and cosine theta can be considered as a constant. So the integral, antiderivative of that one, is the same as cosine theta, is there, and then now 3R squared along with this R, 3R squared is antiderivative in R direction is R cubed, right? And plus, now that is a sine squared theta can be considered as constant, and with R, there's R 4R cubed is antiderivative as now R to the 4. Okay, so yes, R is from 1 to 2, and d theta. Okay. So from here, we can evaluate the value. Then r is now 2, then 8 minus 1, r cubed. There's 8 minus 1 is a 7. So there's a 7 cosine theta, and plus r to the 4. Now 16 minus 1, which is 15, and sine square theta and the theta. Okay, let's see this one. Cosine theta. Cosine theta from 0 to pi. Theta is moving from 0 to pi. And cosine theta itself will be halfly positive and halfly negative. Okay, let's try to draw the graph of cosine theta. That is coming here and down like that, and then this is pi. So if you try to get integral from 0 to pi, then this area, that area, cancelled, so it will become 0. Okay, so because of symmetry, we can ignore that one. Now, we focus on this one. So that is the same as here, 15 is a constant, and integral from 0 to pi sine squared theta. For this one, now we have to use the formula. Earlier, we considered the formula for this sine and cosine square, which is same as half and 1 minus cosine 2 theta. Can you remember that? Okay, so it's d theta. This one has half, two component, half and half of cosine 2 theta. Now, theta is moving from 0 to pi, then 2 theta must be moving from 0 to 2 pi. So for this portion, it makes one whole cycle. For cosine function, once it has a whole cycle, then again, halfly positive, halfly negative, so that the integration will be 0. So we ignore this portion. So there's a half. Now, so the 15 and constant half, and interval length is pi. So eventually we get final answer 15 pi over 2. That's the final answer. Okay. Find the volume of the solid bounded by the plane z equals 0 and the paraboloid z is 1 minus x squared plus y squared. Let's try to visualize the volume, the solid, and try to get the volume. Okay, there's x direction, there's y direction, and this is z direction. Now z equal 1 minus x squared y squared, and now bounded by plane z equals 0, which means the bottom plane. But this is a paraboloid given this way, 1 minus x squared y squared. And then here, and on the bottom, it has this shape that says, okay, when z equals 0, then from here, there is now 1 minus x squared minus y squared must be 0. That means here x squared plus y squared equal 1. Okay, so that bottom is the circle of radius 1. Here, radius is 1 here now. Okay, so we may consider the solid and defined over the domain, which is the radius, the circle of radius 1, and having height now given in this function. Okay? So the volume must be here W integral over D. Once we say that is D, then the over D and 1 minus x squared minus y squared. So we have to get that one. Okay. Now, the bottom D is a polar region. R is moving from 0 to 1, and theta is from 0 to 2 pi, right? So the volume in polar coordinates, okay, angle is from 0 to 2 pi, and R is from 0 to 1. The integrand, 1 minus x squared minus y squared, which is same as 1 minus r squared. And we have here aerial components, which is r, dr, d theta, right? Okay. From this one, integral from 0 to 2 pi, and that one is r minus r cubed, is antiderivative as r. From r we have half r squared, and r cubed from this one 1/4 r to the 4, that r is from 0 to 1, the theta. Okay. From this one now from 0 to 2 pi. Okay. Once r is 1, then half minus quarter, so that we have a quarter, right? And d theta, this is constant, so that we have constant times the interval length, 2 pi. So we have pi over 2, the final answer. Okay. That's the final answer. Now, from this integral, you may observe here, okay, for this inner integral, if you consider that is theta independent, or you may think of this one as separable function, so that from this one, now you may think here from 0 to 2 pi and d theta times integral from 0 to 1. Now that is now r minus r cubed dr. You may consider in this way, this is a theta independent, so that, or separable. In theta direction, the function is 1. So immediately for out integral, rather than writing that integral in d theta, this whole thing becomes now 2 pi, right? And then here inside this evaluation is quarter times 2 pi. You have the same result, pi over 2, okay? You can simplify the calculation. Okay, we'll continue in the second part. Thank you.